Good morning. This is mini lecture F1, and we're going to cover some ideas about distance scales. Uh, and let's start with one of Galileo's most famous quotations from his writings. He's, his conviction was that nature is like a book that you can read, and it's written in a mathematical language. So a natural consequence of that is that you want to work with measurements and calculate with measurements. So he said, measure what is measurable and make measurable what is not so. And so that's what we're going to talk about. And the first thing that when you have a measurement of some mass, some distance, and calculate some energy, some temperature, you always want to ask yourself a question like this. This measurement, is it large compared to something else? Large compared to what? Small compared to what? And this is an essential question that scientists have to grapple with all the time because it helps you understand in this way with your measurements how certain physical objects are related or maybe not related. Now let's look at some examples here. Now these are terrestrial examples, i.e. from our home planet. And we'll start with, a football field. That's about 100 meters distance from end to end. And you can compare that to, for instance, up on campus, the distance from the front door of the library to the front door of Milliken Hall, right across the reflecting pool. That's about 102 meters, according to Google Maps, anyways. Um, Now, here's another thing that you may recall from about 8 years ago. That big meteor that blasted through Siberia, near the city of Chelyabinsk, and destroyed a lot of windows and stuff, and a lot of people recorded it. It's known as a super bolide or a meteor, probably a fraction of a comet from that originally was much larger. And when it entered the atmosphere, they estimate it was about 200 meters. So that's on the order of a couple of football fields in length. And if you think about a football field, double it. So it might be a little bit bigger than Bright House Stadium, put it that way. All right. And so that's comparable to earthbound things. All right. Another earthbound thing is, or not earthbound, but man-made object, terrestrial object, is the space shuttle. That's about 33 meters in length. And so this 747 carrier looks about double that length. So, that's one of the things. So you think about a football field and you think about other things like that, Chelyabinsk meteor or the space shuttle, any number of things. You know, um, they're on the order of 100 meters. And so we would say that they're similar distance scales, or in the case of um, the space shuttle and the Chelyabinsk meteor size scales, because those things they're not distance. Well, there's the distance from end to end of the space shuttle, so we usually call that a size. Anyway, um, so here's another terrestrial example: 2 kilometers distance, and we're going to think about things around UCF. Now, 2 kilometers is 2,000 meters. All right, now that's an easy walk, a little bit more than a mile. Right? And there's a distance comparison right there. And if you work out the calculations, um, the distance to Wendy's on University, just down the road, is about 2.3 kilometers. So that's, and many students that blaze out of UCF 3, 4 o'clock in the afternoon pass right by Wendy's. And so that's about the same. That's a little bit more than 2 kilometers. It's about 2.3. All right. So those are roughly comparable distances. Okay. And if you compare it back to a football field, It's about 20 football fields. Now, normally you don't see things 20 football fields lined up in a row, but you do, drive that distance. That's about the distance to Wendy. So it's something to, kind of get your mind halfway around when you're talking about a couple kilometers. Now you can also compare it to another impact on the big disastrous one down in the Yucatan, and they call it the Chicxulub impact, or they don't know if it's a comet or an asteroid, but whatever it was about 11 to 90, somewhere between 11 and 93 kilometers in diameter, which is why it was so disastrous. This is the one that they think um, extinguished the dinosaurs, 65 million years ago, approximately. All right, so those are all on the order of kilometers. So, a scientist would say, well, that's on the order of a few kilometers. You might be meaning this. Now, Chicxulub is a little bit bigger. You might say, well, the Chicxulub impactors maybe on the order of a few dozen kilometers. So that's a little bit bigger in size. And you might say that the distance from Wendy's is on the order of, a few dozen football fields, 2 kilometers, a few dozen football fields. Right. So that's one of the ways that scientists talk about distances and lengths and mass. You don't have to be talking about distances. You could be talking about energy scales, mass scales, any kind of measurement that you make. You want to think like this. All right, now let's do some astronomical examples. First good one is the Earth-Moon distance. Now we've known this distance for hundreds of years, about 200, with more and more accuracy, um, about 240,000 miles, 384,000 kilometers. And here's a diagram of that distance. Um, it's about 1.28 light seconds. Now, a light second is the distance that light travels in 1 second. And if you ever listen to like recordings of the Apollo astronauts, you can see a time delay, or you can sense a time delay, and that's because it takes from Earth to Moon. When they're up there on the Moon, and they're communicating with Earth, it takes 1.28 light seconds for their radio signal to get back to Earth, and then when Mission Control talks to them, it takes 1.28 seconds. So there's that delay, and you sometimes see that in the like on the news. You're watching the news, and somebody's in Europe or China or Australia, and they're communicating by satellite. There's usually a delay, but it's not 1.28 seconds, but it's a noticeable delay because the satellites are the communication satellites, which we'll study this semester. They're out there a good distance, all right, and not quite 1.28 light seconds. Anyway, so those are three different measurements for the Earth-Moon distance. Another one that Sir Isaac Newton used was Earth radii, and it's about because they knew, they could work out the geometry, um, and so they knew that it was about 6 Earth radii away from Earth, and that was important in his theory of universal gravitation, which we're studying this semester. So he worked with ratios of Earth diameters, Earth radii, and he really made it pay off with his theory of universal gravitation, and you can read about that in the textbook. Now, uh, I want to give you some information about the actual way that I diagrammed this. All right, it works out that there's about 618 kilometers per pixel in my drawing diagram. I calculated it this morning. All right, and so I can get everything into the same diagram. And this one shows not only the distance correctly, but also the diameters of both objects, the Earth diameter in blue, and then that grayish one in the upper right, that's the moon. And that is roughly the correct distance and diameter. So The diameters and the distances are in the same scale. Right? So if you were to, get in a spaceship and back, and travel away from Earth a good distance so that you could see them both, they would look like this. All right. And so, um, and this is not, it's not easy to do. Some astronomical systems, as we're going to see, um, don't show uh, true proportions. And in fact, a lot of times people make diagrams of the Earth and Moon that are out of proportion. And I'm going to show you some of those now. Here's the two on the right are actually from NASA. And the diameter of Moon and Earth are not in proportion, and also their distances are way out of proportion. Now, the exception is the upper right diagram. Those diameters are okay, but the distances are bleeped up majorly, so it's very bad. So what you know, something like this, um, you want to, kind of avoid doing that because it's bad. Unless you clearly state that it's not to scale, and none of these diagrams did that. So scales are important in making diagrams. Now, these diagrams are helpful for teaching certain things. I mean, it's not essential, but you should make a note of it in your diagram that it's not truly to scale. I mean, because you can, these are all about phases of the moon. Gibbous moon and full moon and new moon and all that stuff, which is important. Now, the one down in the lower right is even worse because it shows the sun about the same size as the moon, which is completely out of town. All right, so you got to watch that and try to be careful. All right, now here's another astronomical example that I want to take a look at: the Earth-Sun distance, and the sun's diameter. Now, um, we all know, I think everybody learns in like sixth grade or something, seventh grade, that the Earth-Sun distance is 93 million miles. In kilometers, it's about 149.596 million kilometers. And in light seconds, that's about 499, 499 point something. All right. And now, if you think about diameters, however, it's about the distance is about 215,029 solar diameters. Now, over here on the right, I put this is another diagram that people at NASA um, put together. It shows the Earth, that little blue circle, um, in correct proportion to the sun in the lower right corner. And but the distances, of course, the Earth's not nearly that close to the sun. We're way further away. That's the problem. All right, we're actually 215,029 solar diameters away. All right, so we got a problem with this one. All right, you can't diagram the Earth and Sun and keep their diameters, which are not bad. 109. The Sun is about 109 times bigger than the Earth, so that's not too bad, and you can get it into this diagram. But you can't get the distances, the orbital distance correct. So keeping orbital distance, sun's diameter, and Earth's diameter in the same scale like we did with the Earth-Moon system, it's rough. I mean, you can't, if you actually want to see the sun, much like, and the Earth is even smaller. So if you give 1 pixel for the sun, what do you can't make, and then the line is going to be a minimum of 1 pixel or maybe half a pixel. That ain't going to cut it. All right, so it's tough to diagram. And the word that we use for this is that distance and diameter are incommensurate for this example, for this system, the Earth-Sun system. Now, Earth-Moon is fine. We can get that in there, and Sir Isaac Newton made good use of that. All right. So in this system, light seconds is not bad. That's a good distance scale because you only have about 500 of them. instead of, like 93 million miles. It's tougher to think about intuitively. Uh, and the last thing I want to mention here is just to recall that the Earth diameter and lunar orbit were about 60 to 1, and that's good. So we would say that the Earth diameter and the lunar orbit are commensurate, right? And that's important. Now let's do some atomic examples from the quantum realm of the atom, and we're going to look at the hydrogen atom. Okay, now then we have various ways of measuring parts of the atom, and one of the things that we've done is measure the positive charge of the proton, and that positive charge distribution is about, in other words, the proton itself is about 8.414 times 10 to the minus 16 meters, which is a tiny, tiny fraction of a meter, right? And over here to the right, you can see some carbon atoms and hydrogen atoms arranged into to 3 benzene rings. This is one of the very first images that scientists ever captured of actual molecules. Because they're so small, you don't really, normally you don't really photograph. Well, until recently, you didn't really photograph them, but these guys figured out a way over there at Berkeley. Anyways, so the nucleus of a hydrogen atom is a single proton, about 8.414 times 10 to the minus 16 diameter. Right now, the single electron or an orbit for the hydrogen atom, we haven't been able to measure its radius in any way. I mean, we know it can't have zero radius, but we haven't been able to get precise enough to actually measure its diameter. So we just leave that blank. We know it has mass. It's a lot smaller in kilograms than the proton. We know it has charge, opposite charge to the proton. But we haven't got an estimate of its size yet. Now we do know the relative size of its orbit. Okay, now this is called the minimum orbit. The minimum allowed radius is called the Bohr radius, and which is named after a famous physicist named Niels Bohr about 100 years ago. Is when he figured it out. And that's about 5.291 times 10 to the minus 11 meters. Now, for those of you that have had biology class, you may have had or read about things that are measured in angstroms. An angstrom unit is 10 to the minus 10 meters. And so this Bohr radius, let me back up. Some biological objects can be measured in angstroms. They're pretty small, but they're not this small. And the Bohr radius, 5.291 times 10 to the minus 11 meters, that's about 0.5291 angstroms, so about half an angstrom. So that radius is pretty small, right? And so we've been able to figure out those two measures and other measurements, um, with careful experimentation over the past 100 years, all right? But those two distances, if you look at them carefully, which we're about to do, we're going to run into problems. So let's take a look at that. All right, so here are the two radii, the Bohr radius and then the single proton radius. Now, the ratio of those two, the Bohr radius divided by the proton radius, is about 62,833. Right, so this is another one that is impossible to diagram out and still be able to see any, either the electron or the proton, and it's rough, at least with my graphing software, and then I've got, my drawing program is about 1920 pixels by 1080, so I can't hack this, but there's probably software to do it, but then you'd have to exaggerate the size of the proton in order to actually see the proton. So it's rough. In other words, you can't really see something. You can't really see 1/62,000th of something. You can see a half of a something, you can see a tenth of something. But to say, well, that's about, 62,000th of something, that's kind of shaky. All right. So we would call those two incommensurate as well. And here's the, you know, that's tough. These distances are so disparate that, it's hard to, get a handle on them in terms of the distance scales. But in addition to that, which we're going to learn about this semester, the electron and the proton both behave like waves. Their wave properties are very pronounced at that distance scale. And so they don't behave like solid objects, like the Earth and the Moon. But like 100 years ago, when they were first figuring out all this stuff about the atom, the hydrogen atom and stuff, we did think of the atom, and we still think that way, in a colloquial sense or a simple sense, as a planetary system, a little electron zipping around on an orbit, and then the nucleus, a proton, or maybe a few protons and neutrons for other elements, like the sun, and the electron like a planet going around on its orbit. But it turns out, the wave nature of the electron and the proton make things a little bit more complicated than that simple planetary. And we still use it and we still diagram it and stuff, but it's pretty complicated. I'm going to teach you a little bit about quantum theory on this semester, toward the end of the semester, so it's going to be pretty good. So that's all I wanted to say for today about distance scales. So let's go to a summary and make some summary comments. Now, one of the things that I want to mention to you, don't worry about memorizing all those numbers of, radii and orbits and all that stuff. If I wanted you to use it, you're not going to need that for the midterm. And if I did want to put it on the midterm, I would give it to you. I would write it out for you in a little table. I wouldn't want you to memorize it. But I do want you to think about stuff. And let's take a look at some ideas that I do want you to remember. And that first one is, as I said, always ask yourself, is this distance or mass or energy that I've measured, is it large compared to some other well-known scale? Like the Earth-Moon system. So if you're talking about satellite orbits, okay, how big is that in terms of Earth radii? How big is that in terms of the Earth-Moon orbital distance? Satellite, guys that are designing satellites are going to be thinking in those terms. Okay. Another way to ask this same question is it small compared to some well-known scale? So that would be like, okay, the hydrogen atom is half an angstrom, and that's going to be small compared to just about everything in the universe. But biologically, it's going to be small compared to the things that you find inside of a cell. Okay, now the membrane of a cell, the lipid bilayer and all that stuff, that's going to probably be measured in angstrom units, and the hydrogen atom is roughly half an angstrom across. So those are maybe commensurate. Okay, but you got to ask those kind of questions. Second idea that I want you to remember is that when you're talking distance scales, mass scales, energy scales, etc., you're talking about ratios of two measurements, or maybe you're making several ratios if you have more than two measurements. All right. So, like for the sun example, we have the Earth's diameter, we have the sun's diameter, and that was okay, 109 to 109 times bigger. The sun is 109 times bigger than the Earth. But then the distance scale, we couldn't get that all in there. Okay, we couldn't make those things commensurate, so that was a problem. All right, so you're always going to want to talk about ratios, at least one ratio, when you're talking distance scales. Um, and then there's the vocabulary term commensurate and incommensurate. Okay, that means that the distance scales are compatible In other words, they're not too bodacious. But if you have something that's really bodacious, like the Sun-Earth system, the hydrogen atom, you would call those at least some of those distance scales incremensurate. Now, if you were able to measure the size of a neutron, you'd probably find it as similar to the size of a proton. And then those two diameters, those two distance scales might be commensurate. But the electron orbit and the proton diameter definitely are not. Okay, so those are two vocabulary terms you want to remember, commensurate and incommensurate. And then fourthly, if they're commensurate or not, that tells you something. It tells you something important. And we're going to see that um, in this class when we compare the electrical force and the gravitational force on the electron in the hydrogen atom. Because we know the distance and for gravity, and we know the masses fairly well. And so we can compute the gravitational force between the proton and the electron. And we can compute the electrical force between the positive proton and the negative electron. And then we can compare them, and that ratio is going to be important. It's going to tell us something important about those. So again, don't worry about memorizing the numbers that we've mentioned here in this mini lecture. Do remember these four summary statements and tell your friends, yeah, I'm thinking like a scientist now, because this is the kind of things that we think about, and it's uh, it's a good skill to remember. All right. So that's it for today, and this will be on midterm exam 1. So try to review this carefully. I won't have a homework assignment for this, just the lecture. All right. I'll see you in office hours tonight.